Continue. How many of you took Professor Lenstra's discrete math course? Okay. Good. The other ones, like you guys, you know already what I'm talking about because you're math students. So that's why I'm going to talk about relations. And that's something that you have taken in your discrete math course, I'm pretty sure. So what is a relation? A relation is the following thing. You get two sets A and B, and then a relation on A, or a relation between A and B is a subset of the Cartesian product of A and B. That's all there is. That's what a relation is. All right? So, for example, let's look at the relation of neighboring in this classroom. Okay? So, I want to describe the fact that one of you is the neighbor of the other. So this is very simple. The set A is the set of all the students in this classroom. The set B is the set of all students in this classroom, is equal to A. And the relationship is, whenever two people sit next to one another, like the two of you here, I put them into the relation. So it will be a pair that is an element of this R. So each of these tables here gives you one element in the relation. And then you can see, in fact, it's actually two elements because you want to put you first, and then you first, you first. So, the ordering is in this case not important. But this is one way to define the relation of being neighbors. Okay? You can also define, for example, the relation. So, let's look at the case where A is B is equal to Z, the set of integers. And I'm going to look at the following relation. R is the set of all A and B such that A divides B. That's also a relation. It's the division relation or the divisibility relation. So whenever you have an A, B in this relation, you know that A divides B. Okay? So this is what is what the definition of a relation is. Now I don't need anything else other than this. But I can use the relation to come up with a formal specification of a problem. Now the name already says it all. It's formal. So because it's formal, you really need time to digest it. Okay? It's formal. You need time to digest it. And it's not something that comes easy. Let me tell you that. There will be exercises on the exercise sheet on Monday where you have ample opportunity to practice this. So, a computational problem is a triple of things. So the problem is a triple consisting of a set I, a set O, and a set R. So what are I, O, and R? I is the set of inputs to the problem. O is the set of possible outputs of the problem. And R is the relation between the input and the output. It says which input, if I have an input, what are the possible outputs for that input? So it is a subset of I times O. It's a relation between a possible input and a possible output. That's all there is what a computational problem is. Okay, so let's see whether we can, that's the formal specification. So let's look at the problem of calculating the sum of the first n positive integers. So what is the input to this problem? You know, just think of the input. You know, what would I input, what would I give you as input and ask you to calculate something for? What is that input in this problem?
Integer.
An integer n, right? So the set of possible inputs is the set of all positive integers, n. What is the output of the problem? What's the nature of the output? What is it? Is it a tree? Is it a house? Street? What is it? It's a number, right? It's another integer. So therefore, the set of possible outputs is also equal to the set of positive integers. Now, this doesn't tell me which input corresponds to what output. The thing that tells me that, and that's the most important part of a formal specification, is the relation, is the input-output relation. It tells you a pair n and m is a valid input-output pair when what happens? When m is the sum of the first n integers. So the relation is the set of pairs n comma m such that m is the sum of the first positive integers. First n positive integers. That is a formal specification of this problem. So if you get your boss to sign that, and I'm not holding my breath that your boss will sign anything, but let's say he does sign it, you write a program to calculate this, you go back to your boss, and the boss says, well, actually, this is not what I wanted. I wanted to have the sum of the squares of the first n integers, not just the integers themselves. Then you say, well, you know, on the 24th, it's 24th today, right? 24th of September 2010, you signed this contract. And I adhere to the contract, and so should you. So you're in the clear. Also for you, it's important, because, you know, I asked you these questions. What is a possible input? You said an integer. So that's important when you want to write the program that does that. Because you need to know, you know, what data structure do I use? What's the possible output? It's important to know that. And the relation here just tells you what input-output pairs are admissible. Of course, it doesn't tell you how to calculate it. That's a completely different question. Now, this is a more difficult one. So here, I really want you to pay attention. So this is the optimal coin problem. Now, you need a bunch of things that you probably don't know. So if I have a set A, you know, these slides you see come from a course I taught in Germany many years ago. And the pot you see over there, POT, this is actually a German expression. It's a power set. Have you heard of a power set of a set? Ensemble de parties? For those of you who speak French, well, most of you do, of course, but who learned that in French. So, and in German, it's called Potenzmenge. That's why they write pot for it. So it's a power set. So what does it mean? So if A is a set, then the power set of A is the set of all subsets of A. And I put a star if this subset is finite. You know, if the set A itself is finite, there is no difference between these two. However, if the set A is infinite, there is a difference. Okay. Now, what is this optimal coin problem? What are the inputs to the optimal coin problem? What are the inputs?
Coins.
Yes, the set of coins, this set C that we had, the set of possible coins, and there is another one. It's that this number x that we have to represent as a sum of these coin values. So the set of possible inputs is what? Well, first of all, it's a subset of a finite subset of the integers. This is the finite subset of the integers here. This corresponds to the coins, the coin values. And this guy here corresponds to the x. That's the value that we want to represent as a sum of these coin values. So that's the set of possible inputs. I'm not asking you to give me the most economical way of representing the set of possible inputs. Just one is enough. And this is one, for example. Now, what about the set of possible outputs? What is an output of the problem? What is the output of this optimal coin problem? It's the number of coins, maybe also the sequence of coins, right? The sequence and the number. So you know this. Do you know this notation? Do you ever deal with regular expressions? Have you heard of a regular expression? Yeah. I mean, if you work with an editor that actually is worth being called an editor, then you need to know what a regular expression is. So who has heard of a regular expression? Probably not. Some of you have. Okay. So this plus comes from the regular expression world. So A plus is the set of all sequences with entries in A such that the sequence has a length of at least 1. It's not empty. So that corresponds to your view of the regular expression. You put pluses and stars and stuff there. No? Those?
Can you see the definition again?
Yeah, so the definition is there. But I just say it again. So A plus is the set of all sequences of positive length such that every entry belongs to the set A. And that's exactly written in a mathematically compressed form over there. Okay, so possible outputs of the coin problem correspond to exactly n plus, meaning sequences of positive length whose entries are positive natural numbers, positive integers. These are the possible outputs. And now we come to the relation. Right? What is the relation between an input and an output? Well, the input is of this form. So these are the coin values. I'm sorry that I'm mixing now C with A, but these are the coin values, A1 through AN, and X is the value that you want to represent by the coin values. And C1 through CM are the coins that you're picking from this set. Okay? So when do they correspond to one another? First of all, you want that each of these CI belong to this set, because each of the CIs has to be a valid coin value. Second, you want that these CIs sum up to X, because you want to represent X as a sum of these coin values. So far, so good. If I did not ask you for an optimal number of coins, this would be the end of my formal specification. However, I asked you to give me the smallest number of coins that represent X. That makes the formal specification a bit more difficult. Up to this point, this would be the formal specification of the problem, represent X in some way as a sum of these coin values. I don't care how. I don't care whether it's optimal or not. The optimality adds another level of difficulty to the formal specification problem. So the optimality says, if by any chance I find any other sequence of coin values that sum up to x, for any other sequence of coin values that sums up to x, the number of these coin values has to be at least the number that I have found. And this gives you the optimality clause in your contract. Now, if you think that this contract is difficult, try to buy a house. Those contracts are a lot more difficult than this. This is, you have to just learn to parse this thing. Just to understand it, you have to learn to parse it. In order to write it, you just need to know the language that math gives you, this compressed way of writing things. It's not very different than if you studied law and you had to set up a contract. It's not a very different thing. It's just a different language. Are there any questions to this? Because every time I teach this course, this one looks really daunting, very horrible to students. If you have any questions, yes, please.
When you define the AI, which power to the I?
Yes, a to the I means a vector, all the vectors of length I with components in A. Thank you for reminding me. A to the I is A times A times A, I times. But in the script, all of this is defined. So you can, for the notation, what I would suggest is that you print out the script or put it on your laptop or whatever you want to do with it, but then go through the notation things that are not here. There is a whole set of notation things before that, like here, ensemble standard, etc., etc. That, for example, here, this is AN. That's A times A times AN times. So look at this because we will use this notation. Most of them you know already from other courses you have taken. So this is a formal specification of the optimal coin problem. So you will have ample opportunities to come up with other formal specifications. So, by the way, today I'm going to end this lecture much sooner than normal, probably in 5 minutes. So you have the afternoon off. That's the first lecture. So this is, I want to go through a few steps here that you need for an algorithm and its implementation. The first one is a formal specification of the algorithm. I'm not going to ask you, well, I'm going to ask you in this course, but I know that once you have passed this course, you are not going to formally specify problems with the same level of formality that you will learn in this course. And it's okay if you don't do it. However, what is important for you is when you get the problem to completely know what are the inputs, what are the outputs, what is the relationship between the input and the output. What is it that I want to calculate? That's already a pretty large portion of your work. Then typically when you want to design an algorithm, typically what you're going to do is you're going, the problem itself may be very, very big. The art is to subdivide this problem into smaller pieces and then solve those pieces, combine the solution of those pieces together to give you the solution of your problem. So for those pieces, you want to design algorithms for their solutions. Now, if these are smaller pieces, you may be able to use some of the techniques you learn in this class to solve those problems. Now, once you have designed your vision of this algorithm, you need to design things that we call data structures. That's the brick and mortar of your program. How do I map these structures onto real memory, for example, so that I can have fast access to things. And once you have designed your data structures, Then you go into the cycle of implementing your algorithm. You know, this can be a really long and arduous road. So it's not quite so easy implementing it at the end, but at least if you have a very clear picture of what you want to implement, it makes the implementation task a lot easier. Okay? So this is the cycle typically of implementation of a solution to a given problem. Formal specification, again, formal specification, separation of the problem into smaller pieces, designing algorithms for the smaller pieces and for the communication between these pieces, the construction of data structures, and implementation of the algorithms. All right, so I would like to stop for today. This is not going to be the norm, so we will usually always use the fully 90 minutes, but today is the first one. Thank you.